another interesting consequence of Fourier series representation. Now let us say we have two periodic signals z of t and v of t, both having the same period, and if we multiply them together, what happens to their Fourier series coefficients? Okay. So let us observe this. So if we have two signals, let us say that z of t has a Fourier series decomposition ak e power j omega kt, and v of t has a Fourier series coefficient, let us say some bn e power j omega nt. Both have the same fundamental frequency omega because they are of the same period. So now we, let us say, expand them in terms of their coefficients like this. Now let us say we multiply them, z of t multiplied with v of t pointwise. So we can have e power j omega kt So what is this? So this is k equals minus infinity to infinity, n equals minus infinity to infinity, ak bn e power j omega k plus n of t. So when we multiply these two together, this is what we get. M is equal to k plus n. In other words, what are we saying? So the phasor is now j omega mt. Now if you think about it, k plus n can take multiple values but still give the same sum. That is, let us say m is equal to 1. So for what values of k and n we will get m is equal to 1? In fact, it turns out infinitely many. K equals 1, n equals 0, k is equal to 2, n is equal to minus 1, k is equal to minus 2, and n is equal to 3, and so on. So we can have infinitely many possible values of k and n which will give the same phasor. So how many phasors are actually present in this summation? We are over counting their coefficient, right? So we have to count the coefficient for a given phasor only once. So if we find what is the coefficient of m is equal to 1, what would we get? Then we have to add up all the terms here which correspond to m is equal to 1. So what are the terms that add up to get m is equal to 1? So we will say m is equal to minus infinity to infinity. So we have all the phasors that we want. Now what is the coefficients? What are these terms that add up for m is equal to 1? Let us say k is equal to minus infinity to infinity. Okay, let us fix k. If we fix k, then b is nothing but, from this relationship we can say it is nothing but m minus k. Okay, so what have we done here? So we have picked all those coefficients for which we get the same value of m, that is m is equal to k plus n, and here n is m minus k, which is equal to n. So we have picked up all those terms for which we have the same phasor. So these are all put together, give the coefficient of this phasor. So remember, what is Fourier series? Fourier series is simply nothing but decomposing a particular signal in terms of phasors, and we have the set of phasors here. So we need to find out the magnitude of this phasor. So for m is equal to 1, you just put m is equal to 1 in this term, and whatever value you get, that is the magnitude of that phasor. So let us say that this is some Cm, then you have summation m is equal to minus infinity to infinity Cm e power j omega nt. So this is the Fourier series coefficients of the product of these two time domain signals, where Cm is minus infinity to infinity ak bm minus k. So this is very similar to something that we have seen before, but in a discrete sequence, which is nothing but convolution of two discrete sequences. So we have two discrete sequences. So we knew how to convert to continuous time domain signals. So what if instead of being continuous, if it was discrete, you just replace the integral with summation, and then whatever was in brackets you just put it in subscript and get rid of the derivative or the dt term, right, or d tau term, and that's exactly what we have here. So if we have two periodic signals and you multiply them together, then it so turns out the Fourier series coefficient of the product is nothing but the convolution of their individual Fourier series coefficients. When we convolve two signals, we know that the length of the signal extends after convolution. So if I have, let's say, a sequence AK and it has a bandwidth some B and some BK which has bandwidth some C, then when I convolve them, we know that the length now becomes B plus C, or the length increases. Now because the length increases, the bandwidth of the signals when you multiply can increase. So remember when we said the convolution, the maximum length after convolution is the sum of the individual lengths. So which means the bandwidths here can increase when you convolve, and hence when you multiply two periodic signals, the bandwidth can actually end up increasing. So this is the interesting insight that we get from this analysis. When you multiply two signals, even though their bandwidths could be smaller, after multiplication they can increase. They can go up to sum of their individual bandwidths. So this is what we understand by this analysis, where we saw the time multiplication or multiplication in the time domain of two different signals ends up being convolution in the spectral domain, or what we refer to as spectral convolution of their Fourier series coefficients.